This video is the third and final part of recapping and summarising the 12 core skills needed for Paper 1 Chemistry. So the final skills we're going to deal with are identifying redox, understanding half equations, ionic equations, and enthalpy profile diagrams. So the first question is, for the reaction below, identify the element being oxidized, identify the element being reduced, identify the oxidizing agent, identify the reducing agent, and label these. So you should understand, as a really important definition, there are 3 definitions for oxidation and 3 for reduction. Now, the one that you are most likely to be familiar with is with the acronym oil rig. Okay, so oil rig stands for oxidation is the loss of electrons, and reduction is the gain of electrons. Okay, so we can think about oxidation and reduction in terms of gaining or losing electrons. That's going to be important here. Another way we can think about oxidation is we can think about oxidation as gaining oxygen. And so by extension, we can think of reduction as losing oxygen. So oxidizing, the clue is in the name. If something's oxidized, it gains oxygen. An example of that, going back, would be a combustion reaction. Here, ethanol reacts with oxygen. So it is being oxidized because it is gaining oxygen. You can see the hydrogen has gained oxygen here and the carbon has gained oxygen. So combustion is an example of an oxidation reaction because it's gaining oxygen. Another third definition, which is less relevant right now but important, is that reduction can also be viewed from the perspective of gaining hydrogen. And you can flip that on its head and say oxidation is losing hydrogen. So that's another way of thinking about it. So again, another way you could think about this is the fact that the carbon is losing the hydrogen there as just an opposite, as opposed to, you could say it's gaining oxygen. You could also think of it as losing hydrogen. So just a different way of thinking about it. Now, for the purposes of this, we've got zinc and we've got copper sulfate. So in order to understand what's going on, it's helpful to change this into a symbol equation. So obviously zinc metal is Zn. Copper sulfate is going to be copper CuSO4, and we get ZnSO4 and copper. Okay, now when we think about that overall equation, the sulfate hasn't actually changed. What obviously we can see has happened is the copper and zinc have swapped places. So here we have zinc metal, okay, but here the copper, because it's bonded to the sulfate, is now an ion, okay, whereas here it is not. So if I get rid of the sulfate for a minute, I'd be left with zinc plus copper 2 plus goes to zinc 2 plus and copper, okay? So this helps us to visualize a little bit more clearly what is happening. So you can see the zinc is going from zinc Zn to Zn plus 2. And so in order to do that, it has to have lost electrons. So oxidation is lost. So zinc is being oxidized, okay, because it is losing its electrons to form Zn plus 2. And that therefore means that copper is being reduced because copper is starting as copper 2 plus when it's bonded to the copper sulfate and then ends up becoming copper metal here. So copper is being reduced. Now that's what's being oxidized. So zinc is oxidized, copper is reduced. In terms of the oxidizing agent and reducing agent, we basically just swap them around. So we know that zinc is being oxidized, and therefore you can imagine that the other chemical, copper sulfate, is the thing causing zinc to be oxidized. So we would describe this as the oxidizing agent. Okay, zinc is oxidized, therefore copper sulfate is causing it to be oxidized. So we describe that as the oxidizing agent. Well, you can flip that. We know that copper is being reduced, so I could describe zinc as a reducing agent, as another way of thinking about it. So understand that you have the concept of oxidized. Whatever is oxidized is also the reducing agent because it causes the other thing to be reduced, and whatever is being reduced is also known as the oxidizing agent because it causes the other thing to be oxidized. So being able to just spot, is it gaining or losing oxygen? Is it gaining or losing hydrogen? Or is it gaining or losing electrons, is what's necessary to understand whether to identify which elements are oxidized and which are reduced. Now, we're going to see that same thing manifested here in half equations. So understand that we've shown here an equation which is the full kind of balanced equation. Here, I've shown what's known as an ionic equation, which I'm going to come back to in a moment here. So an ionic equation, in this case, I've ignored the spectator ions, okay, which are the sulfate, the ones that aren't actually involved in the reaction, they don't change. But in a half equation, the unique feature of a half equation is that it includes electrons. So we're basically now just thinking about what happens to the electrons in a particular change. So for example, if we go back to ionic bonding here for a moment, which we did in a previous video, then magnesium, when it reacts, loses 2 electrons. Okay, so just to represent this a different way, so magnesium metal, when it forms an ion, will go from magnesium metal to Mg plus 2, that's the ion that it forms, and it will release 2 electrons when it does that. So those 2 electrons will be removed from the magnesium, and that's why you end up with this structure. Equally, sulfur, okay, if you started off with sulfur as an element, it has to, as you can see in this ion, gain 2 electrons to form a sulfur minus 2 ion, which you can see here has to gain those 2 electrons. Okay, so half equations just represent gains or losses in electrons. Now, that means that you need to first off think about whether it's a reduction or oxidation. Is it gaining electrons or losing them? And then what type of ion it will form. So we're doing first reduction of sodium. So reduction of sodium means sodium gaining an electron. So that means we're going to start with sodium. What ion does it form? It starts with +1. Reduction means we've got to gain an electron. And it would form, if you reform, for example, sodium metal, which would be Na, okay, because it's missing an electron there. If it gains one, it goes back to Na. Another example, so oxidation of chlorine. So remember, oxidation is loss of electrons, okay. So chlorine, if it's got an electron, it would be a chloride ion. And if it lost an electron, it would then form a chlorine atom. Okay, now this is not finished, and the reason this is not finished is chlorine atoms don't exist on their own. Sodium does exist as metallic bonding, and so that formula is fine, but chlorine forms, same as oxygen up here, because it's a gas, diatomic molecules. So chlorine forms Cl2 molecules. So in order to balance this, I'll just change that 2 to a green just so you can see the balancing at play, is I have to start with 2 chloride ions, and that means each one will lose 1 electron. So in total, they'll lose 2 electrons, and that will then form a chlorine molecule. Okay. Next one is reduction of hydrogen. So remember, reduction is gain of electrons. So hydrogen, the ion it forms is H+. It's going to gain an electron because it's a reduction, and it will form hydrogen. But again, exactly the same logic we just applied. Hydrogen is a gas, therefore it is diatomic. Okay, so it's H2, and that means we need 2 hydrogen ions and 2 electrons to complete that. The last one is reduction of titanium, and the charge on the titanium is given to us here in the brackets, which is titanium 4. So we would have titanium plus 4, and it's reduction, so it's gaining electrons, so it's going to gain an electron. And, you know, for example, I could just do this to, it gains 1 electron, it goes to titanium plus 3. Like, that would be a valid reduction. But it might go further, so for example, it could gain 4 electrons, in which case it would then just form a full titanium atom. Okay, so obviously I could do different types of reductions there. The key idea is it's gaining electrons. So half equations just contain electrons. They just show whether I'm gaining or losing an electron. That's all they do. This most commonly appears in the topic of electrolysis. The next question, or next skill, is ionic equations. So we're dealing here with write the ionic equation for the halide test, which results in a cream precipitate. So testing for ions is covered in paper 2 and is covered in C8. Halide ions, the test for those is that you would add, say for example, if I'd got sodium chloride in solution, the test I have to add is I add silver nitrate, which is aqueous, and we will form a precipitate. Okay, I'm just going to write this on the line below just for a bit of space. So the precipitate we form in this case would be silver chloride, in the example I'm just showing here. That would be a solid precipitate. And then we also get sodium nitrate, and that would be in solution. So the precipitate is this solid here, okay? And in the case of the colour, okay, you should know that chlorine will form a white precipitate, which is what will be formed here. Cream is bromine. So for the question we're actually dealing with, we have to realise it's bromine that we're going to be dealing with, and if it was iodine, you should know that that's going to form a yellow precipitate. So that's covered in the second paper. But the skill we're focusing on here is the introduction of ionic equations. And so this equation that I've written here as an example first, you can see that whilst you've got all the different parts to it, the sodium and the nitrate just come together and stay in solution. You see, these were aqueous and it's still aqueous here. So the sodium and nitrate don't actually do anything, but it's the silver and the chloride ions that have actually changed. So if I get rid of the spectator ions in this example here, sort of imagine that in your mind, those are the spectators, what you're left with would be silver plus, and that's aqueous, plus chloride minus, that would be aqueous, and then that would go to, as an arrow, I'm just going to draw this underneath again, apologies for the lack of space, would be AgCl as a solid. And so that would show the ionic equation for the formation of a white precipitate, which would be silver chloride. Now the question is to show it for a cream precipitate. So that's us realising that the test for any halide is that we add silver nitrate. So we need to know that as a fact. So we would start off with silver, and that's plus aqueous. Okay. Understand that silver is an exception to the rule on the charges on the periodic table. So all of the transition metals here all have a charge of +2, unless you're told otherwise. And what that means is in questions like this, where you have Roman numerals, that's me telling you otherwise. It's telling you of titanium, it does have a +2 charge, but it can also have a +4. Okay, like that's perfectly reasonable. So there are lots of different charges that the transition metals can have, but they all have +2 unless you're told otherwise, except silver. So silver's the exception. Silver just forms +1 ions. So that's like a fact that you should be aware of as you encounter it, like as you're told it. So I'm telling you now, if you didn't know, silver forms +1 ions, so just be aware of that as like a special case. And because it's the cream precipitate, we therefore realise it must be the bromide ion, and so they will come together and we will form silver bromide, and that will be a solid. And really important in this question, it's an ionic equation because we have ions present, okay, but you do need to include the state symbols because you have to show the formation of the precipitate, which is the solid from two solutions. So that's really important. So with ionic equations, the general rule is that you don't need to include any spectator ions. Those are ions that don't actually change in any way from the start to the end. So what we are left with, like in which this is an example of, would be the net ionic equation, which just focuses on the bits where changes are occurring. Okay. And lastly, to our last skill, and this is included as a skill because it's something that comes up every single year on the exam in one form or another, is being able to draw and label enthalpy profile diagrams. Now there are 3 types of enthalpy profile diagrams that you ultimately have to know how to do. One for exothermic reactions, one for endo, and in the special case of if we used a catalyst, and that can obviously be applied to both. So in this particular question, it's about you just understanding, recognising which one is. So photosynthesis, you should be aware of the equation for photosynthesis. So I'm just going to mention that, well, I'll put it into the question in a second, but it is carbon dioxide and water forming glucose and oxygen. But you should also be aware that photosynthesis requires light, and that light needs to be absorbed by chlorophyll. So energy has to be input into photosynthesis. So photosynthesis is the most common endothermic reaction on Earth. So if we were talking about examples of endothermic reactions, which are very rare, most reactions are exothermic. So for example here, combustion, that's exothermic. But 2 examples, the 2 most important examples of endothermic reactions would be photosynthesis. Because remember, respiration, which is when we release energy, that's most definitely exothermic because it's releasing energy. So photosynthesis is the opposite of respiration, so it's absorbing energy, and that's why light is needed to cause it to happen. So it's the most common endothermic reaction on planet Earth. The second important example of endothermic reactions you should know is a thermal decomposition reaction. The clue is kind of in the name. Thermal decomposition, you have to add heat in order to cause it to react. So you have to add energy again, which is why it's an endothermic reaction. So really, I can change this question a little bit to draw and label an enthalpy profile diagram for an endothermic reaction. So when you do your enthalpy profile diagram, and apologies, I've already cropped my space off a little bit here, but along the bottom axis, you have progress of the reaction. Sometimes you can just put time there, okay? And the y-axis is like an arbitrary scale, but it's the enthalpy or the energy. So remember, enthalpy and energy are nearly the same thing. It's just that chemists tend to talk about enthalpy because it's the energy per mole. So it's just a way of thinking about how much energy is released in a chemical reaction per the amount of moles that you've actually added. Okay, so that's why chemists tend to use enthalpy. But if it's confusing to you, you can think of energy profile diagrams and enthalpy profile diagrams as interchangeable. Okay, they're almost the same thing. So we always start off with a line which has the reactants on it. So you shouldn't just write reactants, you should write the balanced symbol equation for the reactants. So for photosynthesis, that would be 6CO2 plus 6H2O, okay? And because this is an endothermic reaction, the overall enthalpy change is positive. And so the product line, in the case of endothermic reactions, has to be higher than the starting line, okay? So just to show you that for a moment, okay, always going from the starting line, you draw an arrow to the end line, which in this case, because it's higher, the arrow goes upwards. That would show a positive enthalpy change, and that's what indicates it is an endothermic reaction, okay? And we include the products here, which obviously in the case of photosynthesis would be 6O2 plus C6H12O6. Okay, so again, this skill of being able to construct equations and balance them is important later. So that's one really important part. You have to show the enthalpy change overall and show the position of the two energies, like with the reactants and products. The other bit you should include in an enthalpy profile diagram is the energy of activation. And so for this, you have to put energy in to break the bonds to begin with, and then energy is then released in making bonds. So you've got two sides of this hump, the energy to break bonds and the energy released when you form new bonds. And obviously you can see for any endothermic reaction, more energy has to be put in than comes out, which is why it overall ends up with requiring an energy input, okay, which is why it's endothermic. You have to show from your starting line all the way up to the top of the apex of that hump is the energy of activation, which is EA. Okay, energy of activation is the minimum energy required to initiate a chemical reaction. So whenever you're drawing this, you always go from your start line, the arrow to your endpoint, which is the enthalpy change. So if it was exothermic, this line would be down here, and the red arrow would go from there again, down level to that line. And the energy of activation, which is always you draw a hump joining the two lines, and again from the level of the start line up to the top of that peak is the energy of activation. So you can see the energy of activation typically is much greater for an endothermic reaction than it is for exothermic reactions, but you should be able to do both. Now, although it is not relevant in this question, I will mention a third type, which is if you're asked to do it for a catalyst, means you just draw a smaller hump with a smaller energy of activation, because the catalyst lowers the energy of activation required by providing an alternative reaction pathway. So know that that's the third option, and you should be able to do that for paper 2. So this can come up on paper 1 or paper 2, obviously in the rates of reaction topic. So that's it for these 12 skills. They are all integral and important, and if having gone through this, you now can identify clearly any one of these skills that you are struggling with. It is really important you target it, go back, look at that skill in detail, and make sure it becomes a strength, because I promise if you can master all of the skills that are contained on here, you will do really, really well in paper 1, because this is the foundation of everything that you need, and that will follow through into skills that you then also use in paper 2.